In this slide, we try to look at the logistic regression. First, what is logistic regression and how is it different from the type of regressions that we have seen earlier? Logistic regression is a model used to look at the effect of one or more independent variables on categorical outcome variable. In the previous type of regressions, our interest was to look at the effect of one or more independent variables on quantitative outcome variables. But in most of the field of public health, researchers are mostly interested in assessing the relation between the categorical variables, particularly when the outcome variable is categorical, like, for example, exposed and unexposed, and died or survived, or cured or disabled. This kind of outcomes are measured categorically, and then such outcomes are much more treated by logistic regression. Therefore, in logistic regression, we cannot use principles that we have discussed under multiple linear regression because the outcome is categorical, and therefore, for example, the assumption of linearity is not applicable to logistic regression because the outcome is categorical. And as a result of this, we cannot apply the basic assumptions that we have seen in multiple or simple linear regression and logistic regression. Okay, so we will see then how we can really apply those basic principles to logistic regression. Logistic regression is most commonly used in public health in addressing the relationship between health and health-related conditions. Most of it. If you look at the epidemiological study designs, most of the designs are interested in capturing events or attributes of categorical variables. If you look, for example, a case control study. A case control study, we have cases and we have controls. Cases are those who developed the outcome. Controls are those who did not develop the outcome. And therefore, based on this, we try to look at the history of exposure backward. And therefore, this exposure is measured categorically. Therefore, logistic regression perfectly the model which fits to the case control study design. In cohort studies, the same. We assess the risk exposed and unexposed group is our initial point, and then we try to compare the outcome between cases between exposed and unexposed. Therefore, in case control in cohort study also there are situations when we can apply logistic regression, but most frequently also we can apply another form of regression, which is a Cox regression for prospective cohort studies in most of the cases. Therefore, you can see then logistic regression are very wider application. In general, the main use of logistic regression is to predict or estimate the probability that an individual will have the condition of our interest. So you have to remember your binomial distribution, where we classify the outcome as a success and a failure. The same logic works in logistic regression, where we actually assess the outcome of our interest as has occurred, the event has occurred, the event did not occur. Success and failure, the same logic works. Therefore, we predict the probability of success, occurrence of the category that we designate as a success in the population of our interest. That's one main use of logistic regression, prediction of categorical event. Second, logistic regression is also used to assess the strengths of that association. the strengths of association, the strengths of relationship. That is measured in terms of using measures of association such as odds ratios, as you know. In most of the logistic regression model, we report odds ratios. So that's where the logistic regression become very important. What are the principles of logistic regression? The principles are all the same as for ordinary multiple linear regression. In multiple linear regression, we identify independent predictors. In logistic regression, we do the same. The difference is only the fact that the outcome variables becomes categorical. Now, because of categorical nature of the outcome variable, like I said earlier, we cannot apply the principles and assumptions of multiple linear regression to logistic regression because the outcome is categorical. Okay, then that's the problem that we face. So to overcome the problem of not being able to apply the principles and assumptions of multiple linear regression to logistic regression, we have to transform the outcome variable. We have to transform. We transform from the dichotomy nature or from categorical nature into a situation where it exactly exhibits the characteristics of the outcome in multiple linear regression. In multiple linear regression, the outcome is quantitatively measured and it can take any rational number, if you remember. The population regression coefficients, beta values in linear regression can take positive or negative values. Therefore, it can take positive infinitive or negative infinitive values. Therefore, as you can see, we can see it is whether there is a linear relationship as so long as it can take any integer. In logistic regression, then we wish that also the outcome variable in logistic regression demonstrates also the same characteristics as outcome of linear regression. Therefore, transformation will benefit us by converting dichotomic outcome or categorical outcome so that it can take more possible figures or values. Okay, if you see once the categorical variable is transformed into logarithmic function, it can take any value which could be less than 0 or greater than 0. And okay, you see it ranges from 0 up to positive infinitive. That is the benefit of transformation of the outcome variable. Therefore, that's why you can find odds ratio to be less than 1 or greater than 1, and then it can be positive infinitive. That is the benefit of transformation. When we transform, then the logistic regression behaves the same way that the linear regression behaves in terms of its outcome. Therefore, the categorical outcome is converted to a form of linear outcome when it's a log transformed. That's why we need to transform the outcome variable in logistic regression. In logistic regression, the outcome could be of different forms. One, it could be binary, as a dichotomy, or it could be multinomial. The outcome variable could have more than 2 categorical. For example, if you see the outcome, okay, the outcome or the event that happens to a patient who has been enrolled to HIV chronic care, after a year a patient might have died or maybe defaulted or maybe still in the chronic care, and so many possibilities are there. In that case, we call it a multinomial logistic regression. Or otherwise, if the outcome is ordered, if it takes the ordinal form, then we call it ordinal logistic regression. But in this slide, we much more focus on binary logistic regression, which assumes a dichotomy. Method of entering the data. How do we enter data in logistic regression? There are three methods. These three methods have already been discussed in multiple linear regression. There is no difference in that regard. One is simultaneous method, which we call also standard method, where we force all independent variables into the model simultaneously at the same time. This is most commonly used as a method of logistic regression. Second one is hierarchical method. And the hierarchical method is a situation where the researcher try to identify potential notorious confounders and then separately put into a model. And then the independent variables of interest are also separately entered into the model on a second block. So that's a method that we have already seen in multiple linear regression. The third one is stepwise method. The stepwise methods could also be employed in either forward or backward method. Therefore, just to revise what we have discussed in previous multiple linear regression. In terms of applications, exactly the same for logistic regression as well. What are the assumptions? Now, as we have already seen, the outcome variable is transformed in logistic regression. And then what assumptions do we expect to be satisfied when we apply logistic regression? One is a meaningful coding. The outcome variable must be coded. For example, the outcome variable, if it is dichotomy, for example, occurrence of development of a particular disease, positive or negative, then if we are assessing prevalence of certain condition, then when a person tests positive for the condition, then it must be coded as 1 or otherwise as 0. Therefore, this coding is very important for logistic regression. For dichotomy outcomes, the category of interest must be coded as 1 and the other one must be coded as 0. This is because in logistic regression we calculate the probability that a person will be categorized to the category of our interest. So it is a probability. Always logistic regression model calculates probability for category labeled with larger code. Therefore, 1 and the 0 is the code we use. 1 is larger than 0. Therefore, the probability we calculate is always for the category that is represented by 1. Therefore, meaningful coding must not be ignored. Second, the second one is the error terms. The error terms must be independent of one another, and this can be confirmed by scatter diagram of standardized residual. This is the same as the multiple linear regression. The linearity, yes, now once the outcome is transformed, again whether the relationship is represented by linear line can be checked in this as well, and therefore the logit of the log transformed values of outcome variable should be independent of one another and also should be represented by a straight line. Multicollinearity is another assumption that we don't have to forget. Multicollinearity means the correlation, strong correlation between the independent variables. No model in the regression family tolerates this multicollinearity, and as a result of this, we have to make sure that there is no no multicollinearity, and this is checked by looking at the standard error of each variable, and the standard error must be much less than 2. That confirms that the absence of multicollinearity correlation between the independent variables. In multiple linear regression, if you remember, we look at the variance inflation factor, and when it is less than 10, then we conclude that there is no strong correlation between the independent variables. For logistic regression, we look at the standard error, and it must be less than 2. Another assumption is no outlier, and this outlier can be confirmed by looking at the distribution of the standardized residuals. When we are 99% confident, then we don't need to have standardized residuals that are greater than plus or minus 2.58. When we are 95% confident, then we don't have to have a standardized residuals with a value out of plus or minus 1.96. When that never happened in the data, then we can conclude that there is no outlier. Therefore, we don't bother about the violation of assumption. The last assumption is logistic regression requires very large sample size than any model in statistics. So when we plan to use logistic regression, so we have to always make sure that we have sufficiently large sample size, even starting from the planning phase. Therefore, the minimum is that at least we have to have 10 responses for each category. For each category of independent variable. If the independent variable is sex, for example, then at least we have to have 10 responses for male and 10 responses for female in order to claim that the sample size is sufficient. So we have to have, and therefore it depends. Therefore, if we are going to put several independent variables into the model, then we have to make sure that the sample size is so big enough with the ratio of 1 to 10 for each response category. Another most important requirement for logistic regression is the model fitness or goodness of fit. This has to be very critical, has to be checked, and this is measured by Hosmer and the Lim-Shaw test. Hosmer and the Lim-Shaw these are names of statisticians. I think they are still alive and who are teaching in London School of Hygiene and Tropical Medicine. They have contributed large number of books, of course, and therefore this is the suggestion that they forwarded to researchers to use in order to make sure that the model is fit for logistic regression. Hosmer and the Lim-Shaw test must be done only for multiple logistic regression, not for simple logistic regression. It is a kind of chi-square test that tells us information about the fitness between the data and the model that we use. So it tests the hypothesis, the null hypothesis. The null hypothesis says the data is fit. The data is fit to the model. In order to claim or conclude that the model is fit, then we don't have to reject the null hypothesis. Therefore, when we test the Hosmer and the Lim-Shaw model, and then the p-value must be greater than 0.05. And when that happens, we conclude that the model is well fitted. The data is well fitted to the model. How do we do this on SPSS? I think you follow this step. You can see at the bottom of the slide. Analyze regression, binary logistic regression. You go to options and then check Hosmer Lim-Shaw goodness of fit test. That will tell you whether the data is fit or not. Now let us see some examples regarding the logistic regression. Researchers assessed the occurrence of diarrhea among 50 patients and categorized them by sex to learn which sex is more affected by diarrhea. This means, in other words, does the sex affect the occurrence of diarrhea? In other words, which sex category is more likely to get diarrhea? Male category or female category? That is the interest of the researcher or researchers who are doing this kind of analysis. So now, as you can see from the data, there are 50 individuals, out of which 29 are male and 21 are females. Out of 29 males, 5 of them reported diarrhea, and out of 21 females, 12 of them recorded diarrhea. So from this point, when we eyeball, it seems that females are more likely to be affected by diarrhea than males, as we can see. That is just a visual impression. So we are going to test this. And to do this, as you can see, we have only two variables. Diarrhea is an outcome variable, sex is an independent variable. Therefore, we have to run a simple logistic regression. Why simple logistic regression? Because we have only one independent variable. Why simple logistic regression? Because we have the outcome variable, which is dichotomy. Okay, developed diarrhea or did not develop diarrhea. There are two. So to do this, we have to answer this question. The question says, is sex a risk factor for diarrhea? Use alpha of 0.05. So let's do this together. We have the data here, and the data is entitled the log logistic regression exercise 434. So you open your data and make sure that the assumptions that we have discussed earlier are satisfied. One of the assumptions is that the outcome variable must be coded into 0 and 1. It is diarrhea. If you see the original measurement of diarrhea, originally it was measured as 1 when it is yes and 2 when it is no. Therefore, when a person has a diarrhea, it is coded as 1. When a person doesn't have diarrhea, it is coded as 2. Therefore, now we cannot use this to run logistic regression, because you can see the failure is coded with a larger number. And therefore, if we run regression by this code, then the regression model estimates the probability for not having diarrhea. But that is not intention that we are going to do. Therefore, we have to record this. And when we record, then we record those who are negative for diarrhea as 0, and those who are positive for diarrhea as 1. And you can see it is recorded here. See that the 0 is no and 1 is yes. Then we can use this outcome variable to run logistic regression. Okay? So we go to analyze, and we go to regression, and we choose binary logistic regression. Then we transfer the dependent variable, which is coded to the dependent list. As you can see, diarrhea recoded, it says. So we move that to the dependent variable, and then sex to covariate. Covariate means independent variable. For logistic regression, covariate. Covariate means varying together variability of the independent variable alongside variability of the outcome variables. Covariates. So it's an independent variable. Now, once we have put the dependent and independent variables into the respective dialog boxes, then we go to categorical. And in categorical, we move the dependent variable to the categorical covariate. And if we have independent categorical, then we keep them on the first box. Okay, they are covariates. And then categorical covariate. Why we move to the categorical covariates? Because we have to choose the reference. Okay, we reference which one do we compare, male against female or female against male. The default is always the model takes the second row as a reference. But you can manipulate this if you wish to change. And therefore now, if we take the default, the model compare male against females, because females are written on the second row. Yes is first, no is second. So you can change, or you can proceed with the default if you like. If you wanted to change, then you have to highlight the independent variable and then click on change, and then click on first and then change. Then the first one becomes your reference. Now for this time, let us leave the default as is. In terms of conclusion, whether you choose the last one or the first one as a reference, it doesn't make any difference doesn't have any impact on your conclusion. Now we move to the options. Options, we have a classification plot, and then now we don't need Hosmer in the lymph test because we have only one dependent variable, but we have to check for confidence interval for beta for the oscillation. You can also choose a case-wise listing if you suspect outliers. Okay, if you suspect outliers, and you can also exclude outliers by putting a cutoff point, which is two means in terms of standard deviation. In terms of z-score, it is 1.96. Therefore, this is 2 standard deviation. Let us keep the default as is. Now we are done, and then we use the inter method, which is a forced or a standard method to address this question. Okay, so this is the outcome. The case processing, it tells you information regarding what variables were entered and then the number of participants and so on. Just we look at for just as a sake of getting some information otherwise. The next table tells you how the dependent variables was coded. If you have made a mistake, then you have chance to make it, to recognize it at this point. Now the dependent variable is diarrhea, as we know. Then when there is no diarrhea, it is 0. When there is a diarrhea is reported, it is 1. Therefore, this is correct. That's coded the way we wish it to be. The next one is categorical variable coding. How the categorical variable was coded. As you can see, coding parameter, male is 1 and female is 0. This means the one labeled with 0 is a reference. So we are going to compare male against female in terms of diarrhea, probability of getting diarrhea. Now, the next one is what logistic regression does is that it gives 2 types of models. One is the beginning model, or the block 0, and the second one is block 1. What is the block 0? Block 0 is a model that predicts the outcome without getting any information from the independent variable. Therefore, the first, under the block 0, the first table we see is classification table. What is a classification table? It calculates the probability that individual with diarrhea is correctly classified as having a diarrhea. Therefore, it serves as a sensitivity test. However, this is predicted. This is what the model predicted without getting any information from independent variable. Therefore, it is 66, as you can see. What does it mean then? It says that this model predicts 66% of the individuals with diarrhea can be correctly classified as having diarrhea. That's what it predicts in this model. This is under block 0. So after we moved to block 1, then we'd have to, if we see some changes, okay, some changes from 66, probably we begin to think that the independent variable can affect the outcome variable. Therefore, we will see that later on as we move forward. The next one is variables in the equation. No variables in the equation. It says step 0. It is a constant. Therefore, it is only the intercept. There is no any information. No variable is included in the block 0. That's what it is. The next one is variables not included. Our interest is sex. Sex is not included at block 0. Now, most interesting result we have to look at is block 1. Under block 1, now see that the omnibus test is a chi-square test which evaluates the relationship between the outcome variable and the independent variable. And usually we look at the last row, which is a model, and as you can see, the chi-square is 8.7 and the p-value is 0.0. It says that it tells us the overall relationship between the 2 variables. There is significant association. That's what it tells us. So now, when the omnibus test becomes significant, so we have to expect then the independent variable can predict the outcome variable, and that will be seen in the next table. Model summary. Model summary is, as you can see, is Cox and the Snell square and the Nagar case R squares. This imitates exact R squares that we read from the model summary in linear regression. However, we call this as pseudo R's. Why? Because in categorical variable, correlation is not really a direct and appropriate measurement. As a result of this, we call them pseudo R. And they tell us the same information that the R square in linear regression tells us. And therefore, it says, for example, sex explains the variability in diarrhea that ranges from 16.1% up to 22.2%. That's what it tells us. Just we look at the as information. The other one is to likelihood ratio. The to likelihood ratio is simply the probability of correctly identifying a person with diarrhea. Okay. Therefore, as you can see, the magnitude is 55. Therefore, that's a pretty significant figure that we can see. Classification table, it is 72. Previously under block 0, it was 66. Now it is 72. Now we can see a change of 6 units. This means then if this change is significant, we obviously see that sex is a significant predictor of diarrhea. We look at the last table with the variables in the equation. You look at sex, beta value is minus 1.8, and the p-value is 0.005, and the exponent of beta is 0.156, as you can see. Now, beta is minus. What does it tell us? It tells us there is a negative relationship or reverse relationship. That means as you move from female to male category, then being male is protective. It's negative. Therefore, males are less likely to be exposed to diarrhea as compared to males. That's what it tells us. Being negative or positive tells us that information. When the beta value is negative, obviously the odds ratio will be less than 1. Okay? As you can see rightly, the odds ratio, which is the exponent of beta value, is 0.156. How do we find this figure? You simply raise E raised to beta value. E means 2.72, which is a constant. When you raise the beta value to E, then you get directly the odds ratio. So how do we interpret this? It is less. When it is less, it has a protective effect. Therefore, we have to subtract 0.156 from 1 and find it to be 84.4. Therefore, we compare males against females. Males are 84.4% less likely to get diarrhea as compared to females. Therefore, in terms of odds ratio, it is about 84.4% less likely. That's what we report. And as you can see, the 95% confidence interval for odds ratio does not include 1. This time for logistic regression, we don't reject the null hypothesis when the confidence interval includes 1. For linear regression, when the confidence interval includes 0, then we cannot reject the null hypothesis. Therefore, here, since it does not include 1, we reject the null hypothesis. So, sex is a good predictor of diarrhea, then. That's what we can see. But as you can see, then, this is a crude analysis. Therefore, we cannot be very sure whether really sex is really a predictor of diarrhea, because these relationships that we have seen could be simply as a result of role of confounder. Unless we control for the potential confounders, we cannot be very sure to conclude this. That's why always when we do logistic regression, always we have to do adjusted analysis, which is multiple logistic regression, which provides more precise relationship as compared to crude. Okay. That's already been written for you as interpretation and the steps. You can see from your slides. Okay, that's exactly what you have seen so far is already put on the slide for you, and the interpretation as well. The next is example 4.5, using the data named data file for exercises 50, then you test the hypothesis that possession of television and internet, access to internet, do not predict a screening status of HIV/AIDS. The question is, do possession of TV and access to internet affect the willingness to be tested for HIV/AIDS? Okay, is it logical to look at this relationship? Probably yes. Why? Because if people have access to mass media and including internet, probably they get ample amount of information about HIV/AIDS, and therefore that may affect their decision of being tested for HIV/AIDS or not. So this is what the researcher wants us to look at. I think then you have the data with you, and then try to do this, and then see the report or the conclusion. That has already been done for you, as you can see. The Hosmer and the Limshaw test, which shows the model fitness, is as you can see, it's 0.74. which is very high, greater than 0.05. Therefore, we can see that the model is fit. So the assumption is satisfied. The most important table that we have to make conclusion from is from this multiple logistic regression is look at the variables in the equation. If you look at the television, possession of a television, some people have television and others do not. So which group of people are more likely to be tested for HIV/AIDS? That's what you have seen. And as you can see, the beta value is minus. This means that people who do not have televisions are less likely to be tested for HIV/AIDS. Why? This has to be discussed in relation to the existing body of literature anyway. If you look at the level of significance, 0.027, which is very significant. In terms of odds ratio, it is 0.239. This means that people who do not possess television are 76.1% less likely to be tested for HIV/AIDS. Why? Because they don't know the advantage of being tested. Probably they lack some sort of information. As you can see, the 95% confidence interval does not include one. Therefore, this rejects the another hypothesis. What about the internet? Internet, it is positive, the beta value is positive. However, if you look at the p-value, it is 0.2, which is big, and the confidence interval also includes 1. Then internet possession of access to internet does not predict willingness to be tested for HIV/AIDS. Well, why is this so? This has to be discussed anyway. Probably this may be related to the sample size as well. How many people do have access to internet from the respondents? If the number of individuals with access to internet is so small, obviously you don't have to expect a significant association. Why? Because regression requires large sample size, and because of small sample size, it's likely that you don't see any association between access to internet and willingness to be tested for HIV/AIDS. Therefore, always when you find significant association or when you find lack of association, always you have to ask a question yourself: is this real? Could this be because of small sample size? Then you have to answer basically before you conclude, make your generalization. If the sample size is the likely explanation, then you have to discuss this as a limitation of your study as much as possible, so that your finding or your conclusion can be consumed. I think this is all. Hopefully, this could help you at least to understand well how to run logistic regression and how to make interpretation and conclusion from outputs of logistic regression. I think in case you have some questions, still you have my phone and also my email. You are free and feel free to send me your questions through the email, or you can also ask me by call. Thank you very much. Hope I will see you very soon.